Thank you very much. So this and the next talk is about multi-party session types or global protocol. So first I want to explain what is multi-party session types. So idea is very simple. So multi-party session types start from describing global protocol. Global protocol is written for as a coordination among multiple participants. In this example, we have P, Q, R. P is sending integer to Q. Q is sending Boolean to R. This is projected into each local viewpoint. And for example, from the viewpoint of participant Q, it is getting integer and then sending Boolean to participant R. In this way, you can express global protocol, and once this is projected and implemented, process runs safely, type safe, and deadlock free. So this is diagram representation. First, we start from writing global type, and then we project into local types, and then next step is refinement. Refinement is that you define the type specification, local specification with respect to the participant, and then implement process so that you can implement correct process with refinement and then run safely without deadlock free. So what we have done in this paper is that we extended multi-party synchronous session types process with a mechanized proof with non-stack theorem. Two results are proved. Subject reduction. Its types guarantee type safety. Well-typed session reduced to well-typed session. Next is a progress property, and well-typed session terminates or reduced to another typed sessions. And this using co-inductive reasoning over infinite session type tree. This is a key point of our mechanization. And during this, as contribution, we found the flow in the several papers in the multi-party session types regarding to the subject reduction, and which I want to talk about. And the next thing is mechanized integrated with co-inductive subtyping relation over session trees. And then two techniques for mechanization, which my student taught, and we decomposed the balanced tree into finite prefix, enabling inductive reasoning with infinite trees, and also we employed finite list to encoding in log, and then represent the continuation and branching and selection types. So this simplifies co-inductive definition and proofs together. So this is the whole view of the diagram. And so first step is that we have a syntax of global and local types. This is translated to the session type graph, and both global and local types. Process is typed against local type, and then this is a collection of process. It's actually typed by global type. Here is a key point of the multi-party session types. Multi-party session types is behavioral types. So if process move, type will change the shape, but we prove this is closed by mechanization. And this is the whole viewpoint and proved with standard logbook. So what is a session tree? And the important thing for us is that it should be interchangeable between local and global types. So we should carefully think about data structures. So first of all, this is a local type, of the Local type of the session types. First you terminate, or this is input choice, and from participant P, and this is a branching choice, and then you have continuation. Similarly, this is called internal choice or selections and choosing label and becomes TI. So this is represented by this in the local type, and global type is very similar. So what is the difference? It's only this. You have the communication from P to Q globally described. And if you look at this tree is a very uniform representation. And first, internal node is represented by ampersand P or O plus P, and this is a local type. And global type only changing this. And then node is either end or payload type of the constant. Next is the to represent node or continuation. We use script P and C. Of course, we have label represented by choice. That's all. This is very worked for represent infinite tree. So this is a translation rule from syntax of global types to tree that I will explain by example. So this is a typical way to write multiparty session types. We have two choice, and L1 or L2, and L1 is going to infinite loop. And this is represented by tree as you expected, like this. So next, we define the tree operators. There are two key operators here. First, projection. So it looks like complicated, but its idea is very simple. So let's go through this. So first of all, this is the tree of the global type. If you project onto the participant R, and this is because of sender, and generate sender types, and to Q. Similarly, this is a dual, and so if R is input side, this is the input type, and then from P like this. And actually, key point of multiparty session types is that suppose R is not involved with the communication, which means that it is like this. PQ is running here, RS is running here concurrently. In this case, you need to project without changing this, but each choice should generate the same type. And this is quite limited, but this is called plain co-inductive merging, which we mechanized. So in this way, you can generate tree to tree like this. And so final one of the bit complicated definition is that deduction. As I said, G moved to G dash if M, session M moved to M dash. So you need to define deduction over the global type tree. So what it means? So this rule is very simple. Suppose you are doing action. So this is G and G. Action by selecting label K. Then you go to this selecting and then generate the GK. And actually, again, key point is that if this is RS, it's not involved, but you want to reduce the communication between PQ. So this is like this situation. In this case, you are going inside of this prefix. I put the very simple example, RSPQ, and if you want to reduce it, you reduce it, then you can end up so that you remain the previous unrelated reduction. So with this, you can again doing this tree-to-tree projection mechanism. And so now I go to very quickly. So refinement we think is subtyping relation, which is co-inductively defined. And this is selection is covariant and input is contravariant. With this, typing system is extremely simple. And so we have input and output as expected and recursion. And we have also subsumption rule. And key rule is here. And so we have a projection onto PI and generate TI. Okay? And then each participant typed by local type. And this is corrected and typed by global type. And now I explain what we found bug in session types and the literatures, and actually related with this unloading. So this is a corrected rule we mechanized, and pre-congruence reduction rule. So basically, recursion should be unrolled and quietly, like previous talk of the box, you know. We just need to copy it. But this is incas unrolling. And so this is the main rule of the communications. So suppose you have a participant P and waiting choice from Q. Then you have Q selecting P at level. Then this is selected and then instantiated and moving like this. And so what was wrong here is that in high calculus, Robin Milner have discovered if we use structure congruence, we can model recursion very easily. And that is the case. We believed it in this calculus. So we had the this rule inside the reduction rule instead of precongruence rule. But this invalidates actually subject congruence rule. And what is a counterexample? Actually, he discovered. And so let's process P input and output. And if we type unrolling one, T, this has, you can have bulbul, nut, right? But you cannot hold back, of course, because the types are different. And so this is, we should disable. So that is the reason we have precongruence instead of postcongruence. And we imported some recent publication already and fixed. So this means that the mechanization actually always good to find the obvious pitfall of pencil and papers.
So moving forward, I'll explain the proof sketch for subject reduction and progress that we mechanized. To begin with, we start with concepts that we introduce or assume. We start with the notion of balancedness. This is a concept that we favor when we prove subject reduction, as it lets us work with induction on infinite trees. The definition is that a global type tree G is balanced if for every subtree G prime, whenever we have a participant that's involved in that subtree, we have some global K such that every path starting from that subtree always includes the participant or terminates. Essentially, what this means is that we can find a sort of finite prefix that always involves the participant without going on in an infinite loop. To illustrate, this is an example of an unbalanced tree. And this is unbalanced because if you look at participant R, for example, it's always involved in the subtree G, but you can't find a global K where it's part of the sort of continuation on that path. We also define the notion of well-formedness, which we define extrinsically in our formalization, which just says that recursion's guarded, continuations are non-empty, non-bottom, and that we have that global type trees actually come from some syntactic global type, and that G is balanced. We enforce these rules so that we are only talking about trees that make sense in the context of session types, and that these trees don't contain any rubbish. This then brings us to the notion of grafting, which connects with balancedness in the sense that when we have a balanced global type tree and we have some participant where the global type tree can reduce with, we can sort of locate exactly where the reductions happen. And because it's balanced, we can find sort of an inductive prefix that it reduces with. And this grafting puts a hole exactly where these reductions happen, labeling by indexes so that we can fill it in by different global type trees. So we can construct a global tree by filling these holes, and the way we use it is we locate exactly where the reductions happen. And the point is that when we have proofs that talk about global type tree reductions, which is what we do in this proof, we can start with the base case, which is the hole where the reduction happens, and then the continuations become exactly the branching case. So to illustrate an example of grafting, you can look at this one, where we just have some communications between P and Q. And then if we are to fill in these holes with some global type trees, then this corresponds exactly to filling them in with those global type trees based on the index of the holes. And then this brings us to the first lemma, which is essentially what I just said, is that if you have a participant that's part of the global type tree, then you can find a finite prefix that doesn't contain that participant, but every hole that it fills with starts with that participant. So it locates exactly, the idea is that it locates exactly where the reduction happens. From here on, just quick notation, we will represent some continuations of global and local type trees as option lists of sort tree pairs, which essentially is a way we got rid of alpha conversion by putting we assume an enumeration of labels, and then based on those enumeration, we assume that's exactly what the label corresponds to in the continuation, and then it's an option because some labels might be empty. And then we extrinsically force the continuation to be, we extrinsically force the list to end in a sum such that it's representation independent. With this, we have a lemma that talks about what happens with a global type reducing based on a projection, which this lemma essentially just says that if a global type projects with participants P and Q, and has continuations corresponding to T and T prime for a specific n, then after the global type reduces, that's exactly what the local type projection corresponds to. And we also have a lemma that talks about what the global type tree a lemma that talks about the fact that global type trees exist after reductions given certain conditions. While this condition looks tedious, this is essentially what we get when we invert back on typed processes. So it's kind of just a notion that we write abstractly, but it's essentially saying that if you have a global type that projects onto certain local types which are typed somewhere, then there exists some global type tree that it can reduce to. This brings us to the subject reduction theorem, which states that if you have a session that types the global type tree and the session can reduce, then you can find a global type tree that types that reduced session, and that global type tree also reduces to this G prime. The proof sketch is essentially that if you have a global type that projects onto certain local types. By inverting on the type, you can use the second lemma that I explained in the previous slide to extract some G prime. And then you can use this G prime to find exactly what the local type it should project onto is. And it works very nicely in the sense that we can extract exactly what the local type is. And then after that, there's some inversions and substitutions you need to do. But the gist is that the local type that G originally projected on already has information to talk about what the global type tree takes a step into and what it projects onto. And then we also show progress, which says that if a session types, we also show progress. And to show progress, we start with some canonical forms for processes for sessions. This essentially just says that if you have a session that types with a global type tree, if the global type tree isn't an end, you can find P and Q. And if it's an end, the session sort of unrolls into an end. With that, you can prove progress because we kind of just, and the proof is quite simple. You just do a case split on the type of the global type tree, and then this should give you what you need. And then these two, as a corollary, give you non-stuckness because the subject reduction says that you always take a step into a typed thing, and that progress says that you always unroll correctly. And then I'll quickly talk about the design choices that we made. So global types are implemented using inductive definitions because it's inductive, and then global type trees are defined co-inductively. Instead of using function types, we use a list because this just, for the sake of our proofs, this made it simpler. And then when we're working with co-inductive proofs, we use parametrized co-induction, which is the standard technique that we use when working with rock proofs. It's ordinary co-induction parameterized by a relation. And then the greatest fixed point is the ordinary co-fixed point extended by that relation. And then we start with the empty relation, which is sort of what we expect. And then to do this, we use the Paco library, which implements parametrized co-induction. And we use it exactly in the translations, essentially where we do the substitution. And then just terminology is that the bot2 means it starts with the empty relation, and that GTTTC describes what the relation between the global type and global type tree is co-inductively. Yeah. And then, yeah, I think we don't have enough time, so I'll quickly go over this. But we use lists, because we can do induction within co-induction, which makes it easier to prove certain things. But this doesn't let us prove certain lemmas because we can't have co-fixed points that we can't write co-fixed points if the co-induction uses inductive things in rock, sorry. But you can get away, we can sort of fix this by converting it into a function type, but this wasn't needed for our mechanization. And then co-inductive proofs came along when we wanted to show things like bisimilation between projections, and then we add a equality that talks about if bisimilar, then equals, so that we can show that projections are partial functions. And then this is sound because co-inductive types, just modulo extensionality, is function types with functional extensionality. Quickly going over the mechanization effort, this was about 16,000 lines of rock code with 341 lemmas, 117 definitions, 9 of which was co-inductive. And then we had the bisimilation implies likeness equality, and it's open source accessible. I'll show you this link again. And then for related and future work, so our work sort of talks about, our work talks about classical subject reduction with subtyping, which is, I guess, what we did. And then in the future, we want to incorporate full merging into projections and a full formal proof of liveness So the current work uses plain co-inductive merging, but we want to move on to a more expressive form of merging and then prove more lemmas that relate to the meta theory of session types. Yeah. Yes, thank you very much.